Okay. So again, this is kind of an overview. If you want to do something new, you have to know what has been done, and that is very uncommon, I must say. People just jump on an idea and try to work on this, ignoring whatever has been done before. So I had a plan, but no chance to talk about that. We don't have time. Well, as you know, AI has failed, and Ben talked about it in many ways. And people actually have done everything, and they thought, oh, we have nice equations. For example, Eduardo Cayanello, there is a Cayanello Prize. He was an Italian fellow. In '61, he had his mnemonic equation, and he claimed that he can understand all kinds of behaviors, and it's all in his equation. And of course, it hasn't been too much used or too much useful. Fifth generation computer projects, etc., general problem solver. It has failed for many reasons. Now, we were not quite sure why, but, well, in some areas, Ben has already mentioned that, but why has it failed? Was the approach too naive? Have we not focused on applications, for example? And so people just come up with general theories like mnemonic equations, and they are not useful in any particular case, or maybe that's because we don't address the real challenges. Well, there have been very ambitious approaches, as you know, more recently. Cyc, for example, has been in development since '84 and commercialized in 1995, and now the Cyc Corp has published 2.5 million assertions that link 150,000 concepts, etc. for thousands of micro-theories. Now we have the Open Cyc, and PsychML has been potential application for so many years. And I mean, every year I look there and I hope that something has happened. Nothing has happened yet. Well, there have been other very interesting projects. For example, Whole Baby Brain. I remember John Taylor getting very excited about that, saying, oh, now the system is going to learn like a baby. It has been around for maybe 6-7 years. Nothing has happened again. The Open Mind Common Sense project at MIT, which has been just collecting lots of assertions from altogether 40,000 authors, and ConceptNet that came out from this. Lots of projects around that, and quite interesting ones. HowNet, the Chinese Academy of Science, FrameNet in Berkeley, MindNet, and Microsoft. Actually, the translation group was working on lots of interesting projects, mostly focused on understanding of our relations text dialogue. Maybe one of the problems has been that people have been too ambitious. Instead of going the Google way, doing simple things first, but quite well, they just try to solve everything. So we have already quite a number of ambitious projects. If we don't learn from them, we're going to make the same mistakes. Well, language is one of the challenges, of course. You know about the Turing test, and of course the Leibniz Prize. This is the Leibniz medal. Oops, just turns this off instead of turning the laser, right? Okay, that's the laser. The Leibniz Prize has been, well, not doing too well. I mean, really the programs, as again Ben has mentioned, that have won it in the past 10 or 15 years, all of them are based on kind of pattern matching or template matching or contextual pattern matching. So, but that shows that cheating can get you quite far, because these programs sometimes fool the judges, maybe naive judges, of course, and they don't answer reasonably questions, but they can fool the judges. So what other ways of testing, or what other ambitious steps should we define to see that there is some progress? Well, one is a personal Turing test that has been proposed by Carpenter and Freeman, where programs try to impersonate a real person that is known to the individual, and so we want to find out whether that's a real person or not. That's also very difficult. Well, there are all these question-answer systems, and there are competitions in text retrieval conferences like TREC in question answering, and that's something that you can measure quite well. So in this case, in language domain, we can do that. My favorite is, that has not yet been done, that is, we didn't have any larger scale competition. In word games, you can have things like 20 question games where the machine tries to guess what you have in mind. I think it's much better than things like chess, because in chess people immediately said, well, but this is because the machine is so fast and has such a big memory. Now, why should the speed of the machine help the machine guess what you have in mind better than humans do? So can we really make a competition in something like 20 question game with humans? I think that would be very interesting. And that is still much simpler than the other competitions like Leibniz or default Turing, of course, because all you have to do is to know about objects and their properties to ask proper questions. You don't have to know about complex relations. And I think that shows that there will be many applications where the full understanding of the text is not really needed. We just can approach it step by step. Well, intelligent tutoring systems, of course, there are quite a few of them, and maybe some milestones that we can define. In reasoning, we can think about super experts in narrow domains that will still need a lot of general intelligence to be able to be flexible and communicate with people. Feigenbaum has proposed that. And for example, they could reason in mathematics, bioscience, or law, and experts will pose problem and probe the understanding of a system like that. If we could really have a super expert that let's say, a lawyer could not beat, or that could be used as an artificial lawyer, right? So that would be a very nice challenge and quite specific thing that one could work on. In the same direction, but without the NLP, of course, we have the automatic Turing proving competitions at some conferences. In many subcategories, programs trying to prove as many theorems as possible. That works fairly well, but of course they don't have any intelligent interface, so you can talk or argue with them like with the mathematicians. But at least this is something feasible, I see, that you could work on adding proper interfaces to programs that really are fairly good at doing things that are quite difficult and interesting for mathematicians. And in the end, of course, we can then think about making a program which will be a partner that will give advice to humans in their work, and in their work really creative work, like work in mathematics, evaluating reasoning. Now, lots of mathematicians are checking whether their proofs are correct by using automatic programs, right? But here we want to generate also creative ideas and find interesting associations. So general AI must, which will be general theorem provers, and perhaps some meta-learning techniques which will specialize in many subfields, like right now the ATM programs at these competitions. So that there will be like meta approach, where we have lots of specialized modules for different branches of mathematics, but overall the whole system becomes quite generally intelligent mathematician in a way. A big challenge, of course, is in the genomic pathways databases, in general, in understanding the biological systems, because this really is clearly something that human minds is not able to do. We have hundreds and thousands of reactions every second. I mean, I have some colleagues working on bioinformatics, they're experts on 1, 2, 3 proteins maybe. You're talking about millions of proteins in a cell. So how do we, well, really handle that? People try to have now symbolic models of different metabolic and genetic processes and just search for interesting papers, and there are people that are curating these databases or knowledge bases, adding the missing information. This can be automatized, and it has been automatized to some degree. So lots of things which are already on the way to real artificial general intelligence. And what will be the real artificial general intelligence? Well, the general purpose systems can be taught skills that are needed to perform human jobs, and then we can measure which fraction of these jobs can already be done by AI system. This has been proposed by Nielsen, but in fact Turing already talked about child machine that will learn things. The knowledge-based information processing jobs, for example, can be somehow automatized, and the progress may be measured by passing a series of examinations, for example, in accounting. And I'll show you one example that we have run last year with assigning the ICD-9 code to medical texts, which is done by people that have normally to study 2 years how to do this. And it appears that now machine learning can do it as well as commercial companies. DARPA has, of course, announced a number of interesting challenges and competitions. And, well, humanoid robotics, of course, understanding perception, attention learning, causal models from observations, and hierarchical learning with different temporal scales. The DARPA call on personal assistants that can learn has been quite interesting. The Stanford Research Institute and 21 other institutions are participating in a program, which is a 5 years program, $7 million budget. To create partners for personal assistants rather than complete replacement for human workers. Several other programs associated with this. So, I mean, indeed, people go in the direction that I'll already call AGI. But of course, we know that many jobs already in manufacturing, financial services, etc., has been automatized. But this is rather because of different organization than the AI influence. So we looked at different architectures and we tried to categorize them. Newell has done that in a paper in 1990, where he talks about 12 criteria for, actually also in the book, 12 criteria for cognitive systems. Behavioral, they have to adapt it, dynamic and flexible, development, evolution, learning, knowledge integration, class knowledge base, natural language, real-time performance, and brain realization. Now, only a few architectures have been analyzed in this way, and since we didn't have much space, we have much longer version of this article for a book chapter. We look at the different cognitive architectures, categorizing them as symbolic, emergent, hybrid. talking about the type of memory, whether it's a local or global or rule-based, the type of learning, the adaptive learning, associated learning, bottom-up learning. So I'll be just mentioning symbolic, emergent, and hybrid architectures very quickly. It's all in the paper, so I'm not going to talk about the actual architectures. We have many of the originators of these architectures around among us. Well, the architectures are obviously related to the type of problems that we work on. And, the majority of symbolic, cognitive architectures are based on the Newell's and Simon idea of physical symbol system, which is really much wiser than most people assume, I would say. Well, in symbolic architectures, we have centralized control over the information flow from sensory inputs through memory to motor outputs, and then usual logical reasoning, rule-based representations of perception, action, memory, and then working memory and executive functions, which are stressed, and of course, semantic memory. There are graph-based representations fairly common, which could be semantic networks or variants of that, and conceptual graphs also, frames, schemata, the reactive action packages mostly. The analytical and inductive learning techniques are used. In case of analytical, we have to infer other facts that entail logically from the base of known things. For example, the explanation-based learning or analytical learning type of learning procedures. And the inductive learning, we of course go from examples to general rules. In the knowledge-based inductive learning or delayed reinforcement learning, for example. So there are three potential candidates for agile. Well, SOAR, we have John Laird here, so I won't talk about that. And everybody knows this architecture, of course. And EPIC has been added. This was originally a human-computer interaction model. Has been added and combined with SOAR in quite an interesting way. Icarus by Langley is a newer one, which is also very interesting. Well, John Pollack, who is here, also has defined his Oscar architecture already some time ago. There are, very interesting architecture due to the Taiwan, who is here. The SNAP semantic network processing systems that Shapiro has been working on for like 30 years now is also making some progress and has been used in some interesting applications. Well, so as I mentioned, I mean, it's good to know about them, to look at the references. I don't have time to talk about the particular architecture. Well, the second group is the emergent cognitive architecture, which is much newer somehow. People think, well, we just heard about emergence, right? People think that the intelligence may emerge from some kind of connectionist models, for example, networks of simple processing elements. Now, the memory can be either globalist or localist, meaning that either we have networks which have parameters which are delocalized. That means that all parameters have influence on all the outputs, for example, the typical multilayer perceptions, or we have local type of expansions, basis functions expansions, so like Gaussian expansions, the radial basis function expansions, and other things like that. Well, we may have modular organization and connection models that will create subgroups also of processing elements that react in local ways despite use of non-local functions. Now, there are many learning methodologies. Originally, of course, this field is about learning. Heteroassociative, supervised, and reinforcement learning, competitive learning, winner takes all, winner takes most. The correlation-based learning, like in HAB, using HAB rules that will create internal models. And the complex reasoning behind symbolic architectures, in complex reasoning, these emergent systems are behind symbolic architectures, but then they may be closer if we want to reason using natural perception and try to think using perception. So we have kind of a scheme of the brain, right? We know which parts interact with which, what are the neurotransmitters, etc. We don't know many details, though. I mean, for example, 2 days ago I've heard about this subtle difference between the fear and apprehension that has been now mapped to the specific nuclei in amygdala. So these things are coming slowly, but at least we know quite a bit to formulate some interesting architectures. And for example, O'Reilly and Munakata, Munakata wrote quite a nice book on defining the PDP++ simulator on these biologically based simulations, and then they have formulated the integrated biologically based cognitive architecture, which is using 3 kinds of memories: the posterior cortex memory, which has overlapping distributed localist organization, and the frontal cortex memory with non-overlapping recurrent localist organization, and then the hippocampus, which is sparse conjunctive globalist organization, and that tries to discriminate different patterns, and have defined a certain learning algorithm called Libra that combines the Hebbian learning for learning the structure of the environment with some task-based learning, which is based on kind of a backpropagation, but rather non-traditional. So anyway, higher level cognition should emerge from activation-based processing, and there are lots of psychophysical tasks that the system is capable of, and actually we use it to investigate priming effects for psychologists and several other things, but it's not clear how to scale it up to really large artificial general intelligence. Now, in this field, actually, either you look at very detailed models, which will be spiked neurons, or just try to integrate that looking at a new field. And actually, some very detailed models seem to be also quite useful, but to scale it up, I mean, Blue Brain Project, for example, is using quite detailed models now, and they have a model of the whole column with 100,000 neurons in it now. And actually, they can now, I mean, I've heard a talk a few months ago of a fellow from this group, they can connect tens of millions of synapses from the neuroanatomical data in a correct way in 3D, and have really fantastic tool for doing that. Now, can we abstract some principles from that so that we can understand what is it doing and that we can build that and scale it up to the cortex and subcortical things? That's not clear yet at all, that anything like that will come out from the project. And the project is still missing quite a few things. So, simpler approaches. Edelman's Nomad that has been in development for over 20 years, and there is some new development if you look at their webpage, right? And Cortitronics and the Numenta, I'll talk about this. Anderson has his Emergent brain, and Haikonen his approach to conscious machine. He is in Nokia. There's some other, well, Tosca, for example, which has been recently announced by DARPA, the biologically inspired cognitive architectures program. And there's a group that has worked on comprehensive brain-based model of human learning. So there are some designs for that. Okay. Well, lots of interesting architectures are basically hybrid architectures. The ACT-R is maybe the most famous of these. And Clarion that Ron has worked on more than 50 years now is another famous one. Well, these architectures have been used in a lot of maybe smaller scale projects which are not aimed at general applications, but rather at explanation of some psychological behaviors. The poly scheme is very interesting because it integrates multiple methods of representation, reasoning and inference schemes in the problem solving, where people look at specialist models that will try to capture different aspects of the world, and well, I mean, there are very interesting things you can do with this, but again, no ambitious large-scale applications. That's one of the things to look at. The forecast is a very interesting architecture, which can also not only try to explain what happens in the brain when we reason, but also try to map it to fMRI pictures and tell you which parts of the brain are going to be active. It has a very specific purpose. LIDA, which is Stan Franklin's, we'll talk about the very interesting architecture is called Dual that Boris Kokinov has defined in 1994 and has been inspired by Minsky Society of Mind. Again, looking at, yes, well, I'm looking at him. So there are many others. I mean, Shruti, for example, has been defined by Shastri in 93, but not much is happening. But I think it's very interesting architecture where you look at synchronization of nodes, which represent some processes. Well, the Novamenta engine, of course, then we'll talk about that. So where do we go? Well, we need some grand challenges, I believe, and smaller steps that will lead us to human and superhuman levels of competence, and that should be formulated to focus our research. We can extend small demonstrations in which a cognitive system reasons in trivial domain to some domain that will be of interest to experts, and then that could act as assistant to human expert. This is what is happening. But what type of intelligence do we need? You know that Gardner has defined in 93 that we have at least 7 kinds of intelligence, to be logical, mathematical, linguistic, spatial, logical, kinesthetic, etc. So if you want to have an intelligent jazzman improvising with you. Maybe that doesn't have to be based on general intelligence, it has to be more specialized, but it has to have some base. So how much general intelligence do we really need to make real generally intelligent systems in some specific domain? To some degree, this type of intelligences are independent. And therefore, I think that, AGI doesn't have to be very general. It has to be sufficiently broad to accommodate these different type of things. Well, should the system be really embodied in behavioral intelligence is the answer. I don't know. I mean, Brooks wrote, of course, that elephants don't play chess, but then we know that elephants also don't play chess, right? So maybe they're wise in their own specific way, but they won't play chess. In 2005, there has been an evaluation called agent-based modeling and behavioral representation model comparison of performance of humans versus cognitive architectures in a simplified air traffic controller environment. So there are some tools actually trying to evaluate how far we are. And in 2007, the AAAI workshop on evaluating architectures for intelligence has also proposed certain ideas, for example, creating the in-city driving environments. I think DARPA has done that to some degree, as a test bed, measuring the adaptivity, incrementality of general environments, etc. One idea is to look at the cognitive age that is fairly obvious. We just try to make tests and find out whether systems in different groups of problems are...
We've got to move on if we don't have any time for discussion.
Yeah, okay. So there are different trends that you can try to find out in... oh, sorry. Stop looking at it. There are different trends that you can try to find in what I've been talking about. So let's keep that. Different memory, and we can look at the brain-inspired cognitive architectures as approximation to what brains are doing in many kinds of ways. Again, I don't have the time to do that. But, we try to use this in humanized interfaces and language problems by accumulating knowledge from different resources. And the last thing I'm going to show you is this ICD-9 coding challenge that we had last year that has been done at the conference that I was co-chairing in Honolulu. And basically, 5 groups have beaten 3 commercial companies in the accuracy compared to golden standard of assigning to real discharge summaries very messy texts the ICD-9 codes, which are codes used to get the money from the insurance companies, which is a fairly difficult task. So that shows that we can define some tasks and say, okay, this is a knowledge kind of job, and it's rather difficult to do, but we are at the level already where certain natural language processing systems can compete with humans. So